Hi there. So today I'm going to talk about section 11.1. It's called Power Functions and Proportionality. I'll just call it P&P. Power Functions and Proportionality. Okay. First off, we're going to talk about proportionality. These involve two kind of word problem types, but don't worry, I'll define everything, and the formulas are very straightforward. And then from those proportionality examples, I'm going to generalize and talk about what a power function is and give some examples, and we'll play around with it. Okay? So, what if I tell you the following? That the volume of a sphere is directly proportional to the cube of the radius. Okay? How would we write this in formula form? Okay? Couple things that I want to remind you of. Is in mathematics means equals. Of in mathematics translates to multiplication. Okay? So the way that I would write this as a formula, the volume, I'll call that V for lack of originality. So the volume of a sphere is equals. Okay? When we say it's directly proportional, that means no fractions. Well, what is it directly proportional to? The cube of the radius. So when you say something is proportional to, it's some constant times, then in this case, the cube of the radius, r cubed. Okay? Now, let's contrast that with this example. What if I say the weight of an object is inversely proportional to the square of the object's distance from the Earth's center. Okay, first off, both of these statements are true, okay? Now, when we talk about inversely proportional, that's when you have a fraction. So, the weight of an object, I'll call that W, is, okay, once we see that it's inversely proportional, that means it's going to be some constant, but now it's going to be divided by whatever this is. And in this case, the whatever this is the square of the object's distance from the Earth's center. So if we want to call that D, we have to square him then. Okay? So here are two examples, and again, this makes sense because, again, the weight is dependent upon the force of gravity. Okay? So, when we say something's directly proportional, again, in both cases, K is just some constant. It's going to change from example to example. But here, the volume is directly, so equals K times, well, our radius cubed. And here it's inversely proportional, so it's K over the square of the distance. So, let me say this. In general, a quantity Y is directly proportional to a power of X if Y is equal to K times X raised to some power. And in a similar manner, I will say that a quantity y is inversely proportional to a power of x if y is equal to k over x raised to some power. Okay? So, let me do a couple of examples here. My first example says the following. Suppose C is directly proportional to the square of D. They go on to say if C equals 45 when D equals 3, what we want to do is find the constant of proportionality and then use this to find C when D equals 5. Now, I totally understand that this looks like a lot. We're going to break it down. Don't worry about it, okay? So, let us do this. Suppose C is directly proportional to the square of D. The first thing we want to do is write this as a formula, okay? So, we have C is means equals, directly means k times, well, the square of D, that's D squared. Okay? We've translated our first line. Now, we're given that C is equal to 45 when D equals 3, and the first thing we want to do is find the constant of proportionality. That's our value of K. Okay? So, to find our value of K, what are we given? Well, C is 45 when D is 3. So literally, I plug in C equals 45, I plug in D equals 3. I think you'll grant me that 3 squared is 9, so I have 45 equals 9K. And we can certainly solve for K. K is 5. So, in this problem, I can now rewrite my formula as 5 times D squared because I found my value of K. Okay? Now what we want to do is find the value of C when D equals 5. Well, we can do that. 5 times 5 squared. When all is said and done, we'll get C to be 125. All right, let's take another example. How about for this example, I say now C is inversely proportional to the square of D. And we'll say C is 45 when D equals 3. We're going to want to find the constant of proportionality, and then we'll find the value of C when D equals 5. Okay? So the only difference here is now it's inversely proportional. So now we'll write C is K over D squared. All right. Well, the first thing we've got to do now is find our value of K. What do we know? C is equal to 45 when D is equal to 3. Okay, so now what we have is 45 equals K over 9. How do we solve for K? Well, multiply both sides by 9. So now my K is 405. Therefore, my equation is 405 over D squared. All right. Now what we want to do is the last part. We want to use this to find the value of C when D is 5. So we'll take 405 divided by 5 squared, which is 25. And C here is 16.2. Okay? When things are directly proportional, as one increases, so does the other. When things are inversely proportional, as this increases, this guy will decrease. All right, let us do, how about one more example here? Let me see which one I want to do. Okay. Just give me one moment here. The one page I was looking for is right in my hand. Isn't that always the case? Okay, and so let us do one more quick example. This says ship designers usually construct scale models before building a real ship. It's probably a wise thing to do. It says the formula that relates the speed U to the hull length of the ship is given as follows. So U stands for the speed and L is the hull length. Okay? And they say where K is a positive constant. Okay? The constant K varies depending upon the ship's design. But the scale models of a real ship have the same K. The scale models of a real ship have the same K as the real ship after they're actually modeled. Okay? So, let me ask you this. What we want to know is the following. How fast should a scale model with a hull length of 4 meters travel to simulate a real ship with a hull length of 225 meters that travels 9 meters per second. Okay, so the whole point of that extra little blurb in the problem is that the same value for K holds. Okay, so what we're essentially wanting to find is we want to find the value of U when L is equal to 4. But in order to do that, yeah, we can take the square root of 4 to get 2, but we need to know what K is. Well, fortunately, we were given a piece of information that will enable us to find that. Okay, what were we given? We were given that U is 9 when L is 225. I claim this enables us to find the value of K. Well, first off, I'll do this piece by piece. The square root of 225 is 15. So to solve for K, we have to divide both sides by 15. Now, you could leave it as a fraction, 9/15. You could reduce your fraction, or you can write it in decimal form. It does not matter. Okay? So, I'm a fraction type of person, so I'm going to rewrite my equation now as U equals 3/5 times the square root of L. Well, what do we want to find? We want to find U when L is 4. So 3/5 times 4, the square root of 4, excuse me. So we get 3/5 times 2, which is 6/5 meters per second. or you could say 1.2. Alrighty, so now what I would like to do, since we've played with some of these guys, is actually tell you what a power function is. A power function is a function of the form f of x is equal to k times x to the power of p, where k and p are constants. Okay, in other words, they're just some numbers. X is our only variable. Now, one of the things that people can get confused by is confusing power functions with polynomials. You'll see in a bit when we talk about polynomials, we have limitations on what our exponent can be. In fact, I'll just say it since I brought it up. When we're dealing with polynomials, p has to be a whole number. 0, 1, 2, 3, 4, 5, etc. You can't have a negative number or a fraction. With power functions, we are not limited in that way at all. So, for example, let's ask if some of these guys are or are not power functions. Okay, so my question for these examples is, are the following power functions? And if so, tell me what k is and tell me what p is. Okay, so what if I have this? G of x is, oh, it doesn't really matter, negative x cubed squared over 6. All right, well, when you raise something to a power, well, we can even keep it positive because once we have the squared, it's a moot point anyway, or negative. When you raise something to a power raised to another power, what do? You multiply your exponents. So you could write this as negative x to the 6, or you could just write it as x to the 6 over 6. Why could I ignore that negative? Because remember, when you're raising it to an even power, it's always going to be positive. So we'll ask, is this a power function? And I claim yes. It'll probably look more like one if I bring my fraction out in front. In this case, k is 1/6 and p is 6. All right. Is this guy a power function? Okay, we could multiply this whole mess out, and what would we have? X squared plus 14x plus 49, and then we'd have a 4 in front. But is this of the same form as this? No. Okay, there's more than one term here. Our power function has one term. So, nope. What about this? H of x is equal to 7 times 5 to the power of x. Is he a power function? Nope. Why? Well, yes, you have a constant out in front, but notice this is an exponential function, okay? We needed x raised to some power. Okay, so here my base is my variable, my exponent is a constant, but with an exponential function, those are reversed. All right, what about this one? How about 6x to the negative second times 5x to the negative fourth. Alrighty, well, let's simplify it first. I think you'll grant me if we multiply that out, we're going to get p of x is equal to 30x to the negative 6th. Is this a power function? Yes, it is. My k is 30 and my p is negative 6. Okay? I don't want you to get too caught up in terms of what's a power function and what's not a power function. The real important thing to keep in mind is yet you need some number times x raised to some power. That power can be positive, negative, a fraction, whatever. Okay? Alrighty, so what I want to do right now is I want us to practice finding power functions if we're given two ordered pairs. Okay? I claim this is very similar to the way we would find the equations, for example, of exponential functions if we were given 2 points on the graph. You'll see. Okay? And then what I'm going to do is just talk about some generalities with power functions. All right. So, a power function can be found when given 2 points. And I'm going to do 2 examples. So suppose one of the ordered pairs is 6, 17, and the other ordered pair is 1, 2. Now, I'm just saying, whenever you're wanting to find the equation of a power function and you're given an ordered pair 1, something, in the back of your mind you should be smiling because it means a little bit less work. Okay? Now, first thing is, we know we want to find the equation of a power function. That means I want to find my value of k and I want to find my value of p. Okay, so that's our goal. Now, how do we do this? Well, again, what I'm going to do is notice that I was given a really nice ordered pair. I'm going to plug that in and show you why it is just so nice. Do you agree this says, hey, when x is equal to 1, y is equal to 2? Okay, why is this so nice? Well, what is 1 raised to any power? Isn't that just 1? In other words, that gives us your value of k. So, just by this ordered pair 1, 2, I know that I've gotten this far. I found my value of k. So, the only other thing we need to do here is find our value of p. Well, might as well use the other ordered pair because we know that when x is equal to 6, my function is equal to 17. All right, is this something we can solve? You bet it is. Thank goodness for logarithms. Let's go through and do this. Okay? Notice we have an exponential function here. First thing that I'm going to do is isolate him, just like we have been doing. So I'll divide both sides by 2. So I have 17 halves is 6 to the power of p. Now, if you want to write this as 8.5, go for it. I just tend to keep things in terms of fractions. All right, how do you get to your exponent? Well, remember, when you're looking for your exponent, you take the log of both sides. Okay, so I'll take the natural log of both sides. And if you don't remember why that's so useful, you'll see it in a moment. Remember, when you have the log of something raised to a power, you can bring your exponent down in front. So I claim that my right-hand side is p times the natural log of 6. Well, I can divide both sides by the natural log of 6 to get my value of p. And in case we care, so the natural log of 17 halves, And we'll divide that by the natural log of 6. And so we will get p to be about 1.2. So I claim this power function is 2 times x raised to the 1.2 power. Okay? So hopefully you see that when you're given the ordered pair 1 comma some number, well, with a power function, this number is actually your value of k. So it kind of gets you halfway there. So what I would like to do now is an example where we're not given that nice of information. All right, now again, we want to find the formula for the power function, but now we're given the ordered pair to 12 and 327. Okay, now my technique that I show you is going to bring you back to something that we've done before with our exponential functions. Do you guys agree that, well, if I'm wanting to find kx to the p, from this ordered pair, I could say 27 is k times 3 to the power of p? And for this equation, I get 12 is k times 2 to the power of p. Again, I plugged my ordered pairs in for x and y. Now, what have we done in the past? Notice we've got k's, we've got p's. Remember how we would look at the ratio of these? If we do that, I have 27 over 12. What happens to my k's? They cancel. And then don't I have equals 3 to the p power over 2 to the p power? Now, I'm going to use a property of exponents, which I'll write to the side here. Okay, property of exponents, remember x to the n over y to the n is x over y to the nth. Okay, essentially, normally we start out here and bring our exponent in, but we can go the other way. Do you guys agree then I've got 27 over 12 is equal to 3 halves to the power of p? Okay, can we solve for p? I claim we can. You know what we do? We take the log of both sides. Alrighty. Now, maybe you would be able to look at this right away and already know what the answer is, and I claim you probably can if you reduce your fractions to 9/4, right? 3 squared is 9, 2 squared is 4. But let's pretend our numbers weren't even this nice, okay? Even if we didn't even recognize that 27/12 reduces to 9/4, we would take the log of both sides. So you would take the log of the left equals the log of the right. You would bring your exponent down in front. And then you would divide both sides to get p alone. I claim if you take the natural log of 9/4 divided by the natural log of 3 halves, well, you're going to get 2. So at this point, we know p is 2. We're not done though. We still have to find our value of k. How do you do that? Use either ordered pair. You remember doing this for our exponentials? Okay. Well, let's check it out. I have 12 is k times 2 squared. So 12 is 4k, so k is 3. So this power function is 3x squared. We even know what that looks like. X squared, notice we're multiplying it by 3. Doesn't that vertically stretch it by a factor of 3? Yeah, cool, huh? All right, now what I would like to do to close this section is I want to graph a few functions and I want us to look for patterns here. Okay, these patterns that I'm establishing right now will help us in the next couple of sections when we talk about polynomials. Okay, so what I'm going to do is I'm just going to look at some very general power functions. You've seen these functions before. You've probably never put the label power function to them, but that's okay. All right, so the first power function we're going to look at is y equals x. Notice k is 1 and p is 1. The next one we'll look at is x squared. Here k is 1, p is 2. Then we'll look at x cubed. Then we'll look at x to the fourth, and then we'll generalize. Okay? All right, notice here p is 1. Here p is 2. Here p is 3. And here p is 4. Remember, p is just the exponent. All right. These are graphs that you should be familiar with, but certainly we can figure them out. This is called our identity function, precisely because whatever x is, so is y. Notice it's a line. It's a line with a slope equal to 1 and a y-intercept of 0. We could also just plot points. Well, if I plug in x equals 0, y is 0. If I plug in x equals 1, y is 1. If I plug in x is negative 1, y is negative 1. Whoa. And that's what we're left with. Okay? We just get our basic identity function. All right. We know what the graph of y equals x squared looks like. We've just recently practiced graphing that. Notice if I have y equals negative x squared, it looks much the same. But remember what we learned in chapter 6. If you have a negative in front of your function, that reflects your graph about your x-axis. Okay? Now, y equals x cubed. What does the graph of that look like? Well, remember that's how I refer to my John Travolta function, but we can plug in points. If I plug in x equals 1, well, 1 cubed is 1. If I plug in x equals 2, well, 2 cubed is all the way up at 8. And I think you'll grant me if I plug in 0, 0 cubed is 0. Okay, so there's one arm of my function. Now, if I plug in x equals negative 1, negative 1 cubed is negative 1, negative 2 cubed is negative 8, and this is the graph we're going to get. So that's what the graph of y equals x cubed looks like. In case you want to know what the graph of y equals negative x cubed looks like, well, again, we're doing our reflections because we're putting a negative in front of our function. We're reflecting it about our x-axis. So negative x cubed would look like this. All right, last but not least, if I want to look at x to the fourth, given the level of detail in my pictures, you're not going to see a whole heck of a lot of difference between x to the fourth and x squared. The difference that happens is between 0 and 1 and 0 and negative 1, it's flatter, but then it grows really fast. Now, why is it flatter between 0 and 1? Because again, when you have a fraction raised to a power, it's actually a really small number. Okay, whereas if I had 1/2 in my squared function, I'd get 1/4. Certainly, I think you'd grant me that 1/4 is twice as large as 1/8. Okay? Now, if I was going to graph negative x to the fourth, again, it would reflect about my x-axis. So what is the point that I'm trying to make? What I want you to see from this is the following. Notice when my exponent, when my power is odd. Do you guys agree as x gets large and as x gets small, one arm goes up and one arm goes down? Notice with y equals x cubed. As x gets large, it goes up. As x gets small, it goes down. Even if I reflected it, now it bebopped, but still one arm is going up and one arm is going down. Contrast that when we have an even power. Notice when our power is even, both of our arms are up or both of our arms are down. Okay? This is called end behavior. When people ask about end behavior, they're talking about not what's happening right here in the inner part of our function. They're saying, hey, for end behavior, they're saying what happens as x gets really large or as x gets really small. Okay? That's what we mean. What happens at the extremes? And what I want you guys to see from these few power functions that I graphed is as follows. Okay? So for p being a whole number, when you have k times x to the p, if p is odd, what we know about our end behavior is one arm is up and one arm is down. Now remember, if there's the negative in front of it, all that does is say this arm is down and that arm is up. If p is even, then both arms are up or both arms are down. Both arms will be up if it's got a positive number in front, just like think about y equals x squared. When the number in front of your squared term is positive, your graph opens up. When the number in front of your squared term was negative, we saw that our graph opened down, so both arms would go down. All right, so the moral of the story that I want to get across to you with this last little bit is the following. If the power, let's just call it the power. If our power is odd, that means one arm is up and one arm is down. So it's either going to look like this or like this. If your power is even, then both arms are up or both arms are down. All right, that completes section 11.1. Thanks.